Okay, so this last topic in modern physics that we're going to talk about, or next to last, I should say, is a strange one. Because this topic that we're going to talk about today kind of blends two sciences that you already put together. It's going to be a little bit of physics, which you've been doing all year, and a little bit of chemistry. So today's lesson is this. A little blend of the two. Okay? Where the two topics kind of merge. Okay, so we're going to talk about this. There's a couple of terms that we have to go over, a couple of ideas that we just have to make sure we all have a good basis on. Okay? So what we're going to be talking about today and tomorrow probably are two basic types of reactions. First one is nuclear fusion. I know it's been a while. I know you may not have seen these terms for a bit, but you should be able to tell me what they mean. Okay? What's nuclear fusion? You learned this in chemistry last year. What's a fusion reaction? Anybody remember? Does the term sound familiar? Let's start with that. Yes. Does anybody have any idea what it might be about? When what combine? Two elements. That's exactly what it is. You should have said it. Okay? In a fusion reaction, you take two light elements, you smush them together, and you make one heavier element. So in a fusion reaction, you take two lighter elements and stick them, fuse them together to make a heavier element. Take two lighter elements, okay, and you stick them together to make a heavier element. At least two. Sometimes you can do a couple more. Okay? The other type of reaction is nuclear fission. Okay? Anybody want to talk about that one? Any guesses? If fusion is putting together, what do we think fission is? Splitting it apart. Okay? In a fission reaction, you go from a big, heavy element and you split it down into lighter elements. You start off with a heavier element and you split it down into two lighter elements. Now, if we look at these two reactions, they each have one word in common. What word is that? Nucleus. Okay? The word that they have in common is nucleus. Now, this word is kind of doubly important. The first one is, if you say the word nucleus to somebody on the street, or you were to ask them what it meant, most people would describe what? What do you think? When I say the word nuclear, what pops in your head? Atom bomb, right? Big mushroom cloud, killing lots of people. Japan at the end of World War II, right? All the stuff you learned in history class, all that, right? Maybe a power plant, maybe the one that went like crazy in Japan after the tsunami hit. All sorts of stuff pops in your head. Godzilla, Hulk, all sorts of crazy stuff, right? Stuff you hear about popular culture. And that's not wrong, okay? When we talk about nuclear fission or fusion, we are talking about reactions that give off lots and lots of what? Energy, right? So there is this aspect of energy. Okay, an atomic bomb, super powerful, lots of energy, destroys lots of stuff. Nuclear power plant gives off a lot of energy, can power a whole city. Okay? And so there is that aspect of it. And the thing that we're going to be talking about over the next couple of days is where the heck does that energy come from? Because when these reactions do happen, because it have a lot of energy involved. But remember one of the things that we said about energy, right? When we talked about energy, one of the basic rules for energy is what can you not do to energy? Create it or destroy it. So if these reactions provide a heck of a lot of energy, where the heck does that energy come from? When you see an atom bomb go off in a movie or you see film footage from back in the 40s and 50s when they were testing, you see these big enormous eruptions, lots of destruction. The bomb, for example, the one that they dropped on Japan in 1945, about 9.5 feet long. Right? The other one that they dropped on Nagasaki, I think, was 13. You're not talking like a building-sized bomb, but you obviously saw the devastation and destruction that happened, right? How the heck can something so small create so much energy? Well, that's one of the things that we're going to break down over the next couple of days. Now, like we said, when a common person sees this word nuclear, they think energy and explosion and all that stuff. When a scientist sees this word, a physicist, or a chemist, or even to some level a biologist, although it's slightly different, when they see the word nuclear, it leads them towards another science word that almost sounds exactly the same. What is the other science word that almost sounds the same as nuclear? Nucleus. Okay? Nucleus. Okay? When a chemist or a physicist hears the word nuclear, we think nucleus. That little nugget in the center of an atom. If you're talking about a biologist, that little nugget in the center of a cell. We're not really talking bio, but same idea comes into the head. Okay? Okay? So we're talking about a nucleus. Okay? Well, somehow we have to resolve these issues. Is it about energy or is it about a nucleus? And in fact, it's about both. The energy comes from the nucleus. Okay, so we're going to talk about a nucleus. We're going to have to break it down a little bit. Okay, we're going to talk about nucleus. Okay, so we're going to do a little quick fast 10 that you should remember, so I don't have to reteach this to you. The nucleus of an atom is made up of what? Protons and neutrons. Good answer. It is not made up of electrons. There are no electrons to speak of. Okay? So we don't care about the electrons anymore. Okay? We care about our protons, we care about our neutrons. Now, since we find both of these objects only in the nucleus, we actually have a term for them. We call them nucleons. Okay? Nucleons are particles that you find exclusively in the nucleus of an atom. Particles that you find exclusively in the nucleus of an atom. Okay? Now, when we talk about protons and neutrons, there's usually two things we talk about. The first one is obviously going to be charge, right? Protons have what kind of a charge? Positive. Neutrons have what kind of a charge? Neutral, right? For our purposes, that doesn't really matter very much. Okay? Charge isn't of critical importance to what we're talking about. It lets us tell the things apart, but short of that, we don't really care about charge. We just spent the whole unit talking about charge. Right? Electron, electricity, circuits, and all that stuff. So, the nucleons, the protons and the neutrons, have charge, which is super important, but they also have another measurable quality. What's the other measurable quality that protons and neutrons have that makes them super important? Starts with an M, ends in a dirty word. Mass. There you go. Think about it. That's it. Right? We care about mass. Ooh, look, multiple colors. I don't know. It does it. Okay. The mass of protons and neutrons is going to be super important to those fusion and those fission reactions. Okay? We're going to find out something about it. Okay, so first things first, if we're talking about mass, and this is physics, what are our basic units for mass that we always use? Kilograms. So we need to know what the mass is of a proton in kilograms, and we need to know what the mass of a neutron is in kilograms. Now, considering that a kilogram is about 2 pounds, a little bit more, do we think a proton is even going to come close to 1 kilogram? No. No. We know we're going to be talking about real small mass. But it's a very important mass. It's so important that I don't want you to remember it, but I do want you to remember where you can find it. Where do you think we can find the mass of a proton? Reference table. Reference table. Take out your reference table or access your reference table. Okay? If you look at page 1 of your reference table, okay? And you scroll down on that first page, you will see these 3 values. See if that's here. Here we have the rest mass of a proton, the rest mass of an electron, and the rest mass of a neutron. Okay? We say rest mass because we're assuming they're basically standing still. Once these particles begin to move, then we have to start working with momentum and all sorts of crazy stuff. And it gets a little different. Take college physics and you'll see all that stuff. Okay, so if we look here, here we have the values. Now, we are talking about nucleons. So which one are the nucleons? The proton and the neutron. So we're talking about these 2 bottom ones right here. Okay, now if you look, they have on this chart the exact same mass. What is that mass? 1.67 times 10 to the negative 27. That's a lot of zeros. Okay? Now, for basic calculations, we can almost assume that they have almost the exact same mass. In actuality, there is a difference. You guys should have remembered this from chem last year. Yes, when you did average atomic masses, you figured out what the nuclei would weigh and all that stuff. Right? One of the particles was a little bit heavier, but since the difference was in decimals and it never would add up to equally huge, measurable difference, we just assumed them both to be the same. Yes? We do the same thing here. We assume them to be the same. There is a slight difference, but we assume for our base calculation. If you decide to become a nuclear physicist in the future, you're going to need to know this. Okay, so we have these 2 numbers. Okay? This is going to be super small. Now, you can work with these numbers. You can work with these numbers very well. Okay? But, okay, what we see when we work with these numbers is that they're going to be super tiny, right? Even if you were to multiply that number by 1 million, right? So by 10 to the 6, right? 1 million. You'd still only be 10 to the negative 27. You're still talking a really small number. Okay? So we're going to do something similar, okay, to what you did last year. You worked with crazy numbers last year. Remember mole? 6.02 times 10 to the 23rd, huge number. The pain in the butt to work with. So what did you do? You said, okay, 1 mole is going to be equal to this number. And that way, whenever you did the calculations, you would do 2 moles, 3 moles, 3.5 moles, 4 moles, 10 moles. A little easier to work with, right? And if you needed to, you could always go back to the number of particles just by multiplying by 6.02 times 10 to the 23rd. Yes? Okay, so we're going to do the same thing. Okay? We're going to use a unit that's going to make our lives a little bit easier. Okay? The unit we're going to use is called a universal mass unit. Universal mass unit is very similar to the atomic mass unit that you guys talked about last year in test. Okay? Now, that's a mouthful, universal mass unit. It's a lot to say. So we should just use the abbreviation of a lowercase u. Okay? So when scientists were trying to figure out, they said, okay, we're going to come up with this universal mass unit. It's going to be easy. We're going to make it so that we can measure things like protons and neutrons and electrons in terms of 1U or 2U or 3U, something like that. Yes? Even if it's like 1.01, that's still a number that you can wrap your head around instead of that big, nasty 10 to the negative 27 number. That's just too much. But adding that many zeros and just blank in our brains. Okay? And so what they said is, okay, we'll use a U. But you can't just create a unit out of nothing. Okay? You can't just create something and say, okay, this the following unit. If you do that, you end up with our system of measurement. You end up with a foot. What the hell is a foot measurement? What do you compare it to? Okay, you ask people, say it was the foot of the King of England. Prove to me that that man had a foot that was that big. That's a big foot. An inch. What are these things? Okay? At least with the metric system, there's a tool in the in Europe, the standards and measurements where they say this is the meter. We compare the meter only to this length. The second is this amount of atoms passing a point. Okay? There are standards. The kilogram has a set thing that we can compare it to always. The stupid American system? Yeah, sure. Okay? It's just dumb. So, when scientists decided to create this, they said, okay, we have to figure out what are we going to make this thing equal to? What real life thing can we compare it to so we can say one universal mass unit is always equal to this? And therefore you can compare, right? If you know 1 is equal to this, then when you start talking about 2 or 3 or 3.5, you have something you can compare it to. And so what they did is they took the single most important element for human life on Earth. And they used that as a comparison. So what is the most single important element to all life on Earth? Carbon. Carbon. Everything on Earth is carbon-based. You guys remember organic chemistry? I know, like some of you are going to have facial things. Isomers and all that. Oh, I hate it too. Okay? But you guys talked about long chains of carbon and stuck to a bunch of hydrogens, yeah? You also did that when you did bio. Remember carbohydrates and lipids and proteins and all that stuff? What was it? Large chains of carbon stuck to hydrogen. Right? Sugar, glucose, B6H12O6. Remember these things? Okay? Everything organic, everything living on this planet, including you, is based on carbon. And so scientists said we'll use carbon. Now, when they looked at carbon, okay, carbon has 12 nuclei. Okay? It has, now what do we mean by nucleon again? Protons and neutrons, right? 12 particles in a nucleus. So carbon has these 12 nuclei. Okay? And so what they said is, cool, what we'll do is we'll make one universal mass unit equal to the mass of one of those particles. So what they said is 1U is equal to 1/12 the mass They said we'll make 1U equal to 1/12 the mass of a carbon atom. That's the standard. That's the same whether you're here in the United States, in London, in China, in Sri Lanka, in Tanzania, in Lima, Peru. It doesn't make a difference. It's the same. It's set your clock by it. So it's the same. Does that make sense? That makes it a good standard of measurement. Okay? Now, when we actually figured this out and we did the math, something weird came up. When we tried to figure out, okay, so we know 1U is equal to that, we wanted to figure out, okay, so 1U is equal to how many kilograms? We just wanted to check it out, make sure everything was cool. And what we found was 1.6 10 to the negative 27. Oh, wait, I forgot a number. What should be there? 1.67, right? When they actually did the math, what they found was that. It was 1.66. Okay? Which, when you look at it, you go, it's 100th of a place off. That's not bad. It's pretty accurate. But that bothers scientists. Why was 1/12 of the mass of a carbon atom coming out to less than one nucleus, right? So there are two nucleons with 1.67 and 1.67, right? But when we did the math and we figured it out, we looked at how heavy an actual carbon atom was, and we divided that by 12, real easy math, right? We found out that the number came up to just a little bit off. It's almost like there was some mass that was missing, right? Now you guys remember something from chemistry last year. Did mass just go poof out of existence? Can we just lose mass? No, mass is just like energy, momentum, right? Charge. You can't make it, but you also can't just move it out of existence. Got to be conserved. Or if it's not conserved, it's got to be turned into something else. Okay? So scientists looked at this and they went, something's off here. There's this missing mass. Where the heck did it go? Yeah? And so scientists look, and they look, and they look. Okay? And they started looking at the actual atoms. Okay? And one of the scientists who worked on this problem was arguably the best known physicist in the history of science. Okay? Especially the recent time. Was a man who was alive relatively recently. Okay? He was of Jewish descent from the country of Austria. And he was known to have particularly wild hair, especially in his older days. Okay? Who am I talking about? Einstein. Okay? A full year of high school physics, and we're finally getting to Einstein. So we talked about him a little bit before. We're going to get to Einstein. Okay? At the beginning of the 20th century, okay, the world of physics has changed. Okay? For the previous 300 years, they've been working under several conditions. In fact, for the previous 1,000 years or so, they've been working under like Aristotle, and Newton came around and tweaked it a little bit. Okay? And then at the end of the 20th century, you get the development of lots of ideas of like electricity from like Faraday and from Maxwell and people like this. Okay? You get Planck, remember him? That weird little number of his. Okay? Coming up. De Broglie, lots of these different scientists working. Rutherford, all these other guys. Okay? Bohr, all of them start working. Okay? Einstein being one of them. And so Einstein primarily does his work on light. That's what I do. And when Einstein was in school, during his time, he would sit in the physics classroom. Kids were sitting in physics classroom just like you guys are now. Okay? And they would look at the universe on like the first day of physics, just like you guys had. Then the teacher would stand in front of the room, like I did, and they'd say the universe is made up primarily of two things. One of them you learned about before, one of them we're going to learn about this year, just like I did the first day. The first one, okay, is what you learned about in your cases last year. Okay? It's the stuff in the universe that takes up space. It's the stuff in the universe that has a measurable mass. It's the stuff that has different phases. What is that? Starts with an M and ends in an atom. Wow! So small. Right? None. Okay? And all the chemistry that comes with it. Bonding, bond angles, polar bonds, non-polar. I know. I'll stop so you guys don't all like switch up. Okay? But all that stuff that you learn. Okay? And then the other side of the coin was the stuff your teacher would say we're going to learn this year, or the stuff you guys have learned this year. Okay? And that's the stuff that doesn't have mass, that takes up no space, but likewise is also conserved and likes to make things move. Starts with an E. Energy. Energy. Look, I didn't have to give you the hint on that one. And so you would have learned these two things as two wholly separate things. And it makes sense, and that's how you've learned it up to this point. Matter and energy, matter and energy, matter and energy, two different things, right? They can affect each other, right? If I push on you, you fall over. You pick up velocity, which means you pick up kinetic energy, right? You lose gravitational potential energy. All sorts of things. Okay? And it made a lot of sense, and the world worked pretty well. You could understand basic everyday interactions and stuff like that. But there was one thing that kind of effed up everything. And it was that thing that we said all these scientists have been working on just before. The stuff that's coming out of these guys above our heads. What is the thing that screws everything up? Light. How does light screw everything up? Well, what did we talk about earlier in the year? We said that light has a wavelength. What light has a frequency? Right? It has a period. It refracts. All this stuff can be explained by it being a wave. Right? And waves are how energy gets from one point in space to another point in space, right? Whether it be matter waves or electromagnetic waves or whatever. Cool, that works. And we can explain 99%, or 90% of the stuff that light does through waves. But then we learned about something else. We learned about that thing called the photoelectric effect, right? When the electrons get knocked off. And the only way that could happen is if light acted like a what? Particle. And particles are part of which one of those two? Matter. So the question became, is light a wave or is light a particle? Which one is it? Wave, a particle, wave, a particle, wave, a particle. People are fighting. Scientists literally knock down, drag out fights. You ever want to see something funny? You should see a nerd fight about things like that. Pencils flying everywhere, calculators upside the head. Looks like a WWE match, except really lame, and everybody's out of breath in about 3 seconds. Okay? But they were arguing. Okay? And then they finally came to that resolution that we came to, that light isn't a wave, and it isn't a particle, it's both. It has a, what's the term we use? Starts with a D? There you go, dual nature. Right? Light is both a wave and a particle. Yay! Except here's the problem. When you say something like that, the next scientist is going to follow up behind and go, is light the only thing? Light has a particle nature. So do particles have a wave nature? Does that atom of carbon have a wavelength, a frequency? do you, right? Does that table. And so that one statement of saying that light has a dual nature opens up the question, does everything? And so scientists start looking into it and studying it, one of them being Einstein. And what he comes to realize is, guess what? You're right. Everything in the universe isn't matter or energy. Everything in the universe is matter and energy. They're not two different things that branch off from each other. They're two sides of the same thing. The universe is made up of one thing. Sometimes it looks like matter, sometimes it looks like energy. The big difference between the two of them is ultimately speed. Matter is just energy that's moving really, really slowly. And energy is just matter that's moving really, really fast. Okay? That's what they came to realize. And Einstein ultimately puts it all together into arguably the most famous equation in all of physics. What's the most famous equation in all of physics? The one that everybody in the world knows.
E equals mc squared.
E equals mc squared. The equation that at some point somebody went up to you and said, you want to learn physics? But E equals mc squared. That's so hard. Look at this. Is this the hardest equation I've written on the board all year? For God's sake, it's ridiculous. This is not hard. We will talk about what this means